we have a graph like this where n is the size of the inputs is the x-axis,
It means that
and
this t,
y
that
is
this t of n,
t of n. So generally, the amount of work of the algorithm increases as n increases. It could be linear, it could be a hyperbolic function, something like that. But when we say that t of n is big O of some f of n, it means that the amount of work done, suppose that t of n is this, suppose that t of n is this function, so it's a linear function. When we say that t of n is some big O of f of n, it means that uh, t of n, the function that expresses the amount of work of the algorithm, is bounded above by f of n multiplied by some constant c. So this line is c multiplied by f of n for all inputs sizes that are bigger than n0. This is a mouthful, but really complexity analysis usually comes very, very, very intuitively. And if there's something that you didn't understand in the first lecture, I could go over it yet again. But right now we will see a very cool data structure. Um, so we will see a very, very cool data structure called the segment tree, which is actually an array. So arrays in general are a very, very powerful data structures that a very powerful data structure that could enable some very complex operations with just simple arrays, no additional or no more complex things added to a simple array. And that's what we're going to see right now. So, basics of array, I hope at least we can agree that an array is a contiguous sequence of cells where each cell holds an object, and we could access the values of the cell directly based on the indices. So if we have like if we have like if we have a um, random. Okay. So suppose this is an array that we have. If we want to access any elements in the array, we just need the indices. Most of the languages support zero-based indices. Some supports one-based indices like MATLAB or something like that. But usually most programmers are much more comfortable with zero-based indexing. So this is an array. It's just a contiguous uh, space where each element is indexed directly. So here we go. We're gonna go very quickly about a fundamental flavor of arrays that are very, very useful in programming languages. So if you use vectors in C++, vectors or lists or array lists, These are not. These are actually called dynamic arrays. Uh, the main difference between these arrays and the simple array that we would declare like int t equals new int some size n. Uh, this is a static array where the number of or the space occupied by the array is constant. It won't change size, so uh, we could not add values add more values than n values. We could just put values from 0 to n. So if we run out of space, we can't add another element uh, beyond the indices n minus 1. So we could just put values anywhere from 0 to n minus 1, and that's fine. Uh, Dynamic arrays like vectors or array lists, etc., are inside just simple arrays. But as you add elements and you remove elements, the size of the array will or rather the underlying array will be resized. So initially we have some array T allocated with n cells, so we can put up to n elements in the array. Once we add a new element and we don't have a space to put this n plus one elements in the array, if we don't have space to put a new element, then simply the size of the array is doubled. The original array is copied, and the new element is just put where it should be placed. So the difference between a static array and a dynamic array is that if we run out of space, we just double the size and put the new element inside. This is very useful in implementations like queues. What else? Usually this is how it's done inside, so that you have enough space to put all elements. So just briefly, again, you are most likely never going to implement dynamic array, but for some reason, maybe sometimes you need to have a data structure that places elements inside the collection, and at some point you need to expand the size of the collection because you run out of space. So this is how you do it if you use an array. Otherwise, if you use like a linked list, you don't have to worry about memory allocation. You just continue linking elements until you completely run out of physical memory space. Just a second, looking into my notes. Okay. So let's define a simple data structure dynamic. Initially, we'll define the data structure to be a collection of integers only. EE, based one, meaning if you know MATLAB indexing starts from 1 to n. So if you allocate an array of n elements, the first index in the array is 1. Usually like C sharp or Java or most of the programming languages, uh, indices start from zero. I think also indices start from one. I think R also indices starts from one. I don't remember well. Okay, we're concerned only with zero-based indices, not. Okay, so this is the construction of the data structure dynamic array. Again, briefly, this dynamic array will be a data structure that will resize the array when we run out of space. We will have an array. Initially, we will support just integer elements, and later on, we will see how to create a data that could support any type of any types of values. So integer array. So this is just a static array declaration. Uh, Number of elements. This instance attribute will be the current number of elements in the array. And we have a constructor that would create an array with 16 elements, number of elements equals 0. So this is O1, uh, exactly T of n here of this procedure, T of n is equal 16 plus 1. This is a single instruction. This is proportional to 16. So this is basically 17 instruction. You could see it also as 17 multiplied by n to the power of 0. So we just have 17, and as we saw in the first lecture, what we do is we ignore all constants. So the 17 would be replaced by 1. And that's it. So constant time, running time for this procedure to complete. Okay. Even if even if we start with like 32 elements, with the even if the base array will start with 32 elements or even 1,000. This is still constant time because the number of instruction that will execute here does not depend on any input size, so it's constant time.
Hey, can you guys hear
Okay,
me?
Sazzle and accessing a single element. So here here not it's important not to confuse number of elements
Can you hear me? Hello?
With the array point length, because array
Yes? Hello? Elias?
array is the collection that we will put into it elements. But we could have the array completely filled with elements. So we could have number of elements equals array point length, meaning that the array is completely filled. Oh, you hear me well? Is it bad a little bit? What speakers? Oh, um, oh, um, wait, speakers. I'll just change. Is it better right now? Okay. Um, so it's important not to confuse number of elements with array point length because array dot length because array might be filled, it might be partially filled. So the length of the array does not reflect the number of elements inside the array. So the actual number of current elements inside the data structure right now is held in this variable. We increase it every time that we add a new element. We decrease it every time that we remove an element. So size will just return number of elements. This is constant time, of course, and and uh, get getting a single um wait I will I will I will try to fix it. How about now? Is this better? Hello, hello. I can't hear you.
I can hear.
Yeah, I can't hear you. I can't hear you guys at all. Okay.
Yeah, I can hear you. Yeah, you're right.
And I can hear you both.
Can you hear me? Yeah, I didn't. Yeah. No. Oh, I know. I can hear you. I can hear you now. Okay. Okay. I had okay. Uh can you I can hear you. I think I can hear you right now. Can you talk? No, I can't. I can't hear you.
Please check your microphone, please.
What the hell? Yes. Yeah. No, no, it's not the mic, it's actually the sound. I had the browser. I had the browser completely muted, but okay. Let me just exit and then come back. I will exit the okay. Okay. So up to now we said that this is O1. This just returns the element if the element um, if the element is within the values that are already defined in the array. We just return the array. Otherwise, we just return null. We could implement with the try except clause or try catch to yeah to throw an exception is less than zero above than the number of it's O1. So here is where things gets a little bit more complex. A value like if value to our dynamic array, we first have to check if if the array is completely filled, meaning that the number of elements in the if that's true, then we don't have anywhere to put our new elements. Then what we do is just we resize the array to be length of the actual array multiplied by 2. And this resize procedure, what it does, it's a private procedure that will create a template with the size passed. So we create a temporary array. This procedure copies values of array. This procedure called will copy values from a source array. This is a source array. This is a destination array, and this is the indices. This is the index where we from where we start copying. This is the index where we want to start copying to in the destination, and this is the number of elements that we will copy. So what we're saying here is that copy elements from array from indices 0. We could have specified like from 1 or from half or something, but we need to copy all the elements, the existing elements in the structure, and put it in the new array from 0 to wherever, and we will copy from array all the elements, and in the end we just assign the reference of the new array that contains now all the elements, and that has double the size. Well, double the size for this use when we call the resize with double the length. But if you think about it, if we want to resize the elements to shrink the array, Like if if we want to
I think the system got crashed again. Yeah, it happened even last time. No, no, no.
can you hear me? I was connected? No. Can you I was disconnected for a while or just a minute?
Okay, my mistake.
Okay. Um um okay. Here in the push operation. Okay. Yeah. No, it's not immutable. We are putting elements into it. The purpose of creating an array with double the size is just to allocate more memory so we could place the new element. So we are doubling the size, or we are creating wherever size, wherever the parameter that we are passing to the procedure. We are creating an array, temporary array with that size. Here in push, we are doubling the size. We are copying all the existing elements in a temporary array, and then we pass the reference. All this work is just to, uh, so if we have, um, so if we have this array, suppose that we want to place a new element and at the end, and the array is full. For Python, it's a lot easier, but what we are doing, we are creating b uh, equals like size of a doubled by 2. So this is b. Len a is 10. Len b is 20. Oh, sorry. Yeah. So yeah, so we just doubled the size. So we just doubled the size. So we will have extra space to place the new elements in the data structure. That's all. So That is if the array is filled. If the array is not filled, this will not get executed. We will just place the element at number of elements, and we increment number of elements by one. So this number of elements will always point to us where to place the next elements that we want to push. By the way, there is a note here that this is what we're doing here. We are creating actually a stack, but we could access elements from the middle of the array. So keep in mind that this resize could be used not just only to double the size. We could pass half the size of the actual array to shrink the array. We will see it later. So the point is, if we ignore this, so if the array is not filled, this is O1, constant time O1. But so if initially the size of the array, like initially we had 16 elements, so we could push 16 elements in the data structure, and then when we need to push the 17 elements, we have to create an array with double the size, so an array of 32 elements. You have to copy all the first 16 elements inside the newly created array, and then we need to place the 17th element in its right position. So here, actually, in the 17th push, we have to double the size of the array. And by doubling the size of the array, this is an O(n) operation. This is an O(n) operations. But to get to this O(n) operations, we will do n multiplied O1 operation, and then in the nth plus 1 operation, like I said, we did 1601 operation before we needed to double, and then in the 17th operation, so the O(n) plus 1 nth operation, O(n) operation, right? This is clear so far. I hope this is clear. So, yeah, is this clear? Look, so suppose that we have 17 push call in succession. Initially, when we initialized the constructor, we had 16 cells where we could place elements, right? So in the first 16 push, we could place the elements without any issues because is not filled, right? 17th operation, we have to double the array, copy the original array, and then place the elements. So we have what I just said. We have to double, yeah. Yeah, the last, yeah, the last push, the 17th push, an operation. So the nth plus 1 push will have on operation, but the first n operation, the first 16 operation will be O1. We're clear about this? This is, yeah. Yeah. Yeah, yeah. Okay, that's the exact amount of work, but we are like I said, we don't care about the exact amount of work. The constants are ignored, whether it's plus or minus, or whether it's plus a million or minus a million. Constants are ignored. Here, this operation, this operation, we have to double the size. So we will have to create an array with double the size, so 2n. Copy the elements, so copy the elements of the original array, so n. And then this is a constant time operation. So this is actually 3n. But we will ignore the 3. We will just, this is the exact tn. And this tn is on, because we would ignore the constant factor. Yeah. So what I was saying is that for 17 operation, we did 16 O1. Then let's say 16 single operation, that then 16 multiplied by 3. This is referring to that t, this resize. I just said that t of n is 2n from this, plus n, which is 3n, number of operations. So in 17 push, this is the total cost of all the 17 push, not just the 17th. So this is the total cost of all the 17. We're clear? So we could
Yeah.
we could change this
Yeah, it
17.
makes sense.
We could just generalize n plus 1. So for n plus 1, we do n O1 plus plus on, an on operation. So this is where we talk about amortized complexity. And in amortized complexity, we have a succession of operation where where this where we have a series of operations that cost like O1, or cost something like cost f of n. Here f of n is O1. So we have a succession of n operations that are constant time. Then the nth plus 1 is On. So we just say that in average, so this is the cost of n push, or rather, this is the cost of n plus 1 push, right? So this is the cost of n plus 1 push. So we average the cost of a single push as n plus, let me make some room. So we average the cost of a single push as equal to NO1 plus on divided by n over 2, n plus 1, pardon. So this n01 is actually this is actually on. We could change this to just write it as o, and we have n single instructions. So this is basically on. So we have 2 on over on over something that is on, which is actually just constants. So we average a single push as a constant operation. So we have to make n push in order to get to that push where we pay for all the previous operations that costed really a constant time. Or you could see it as, if this is still confusing, you could see it as we have O1 operation. You have n O1 operations, and then we have in the nth plus 1 an on operation. So you could see it as, by saying that this is on, we mean that this is some c, some constant c here, incidentally c equals 3, some c multiplied by n. So you could see it as if we distributed this cost on all the succession of previous operations. And this will not, we will not do another on operation unless we hit then unless we fill the array again. So unless we place 2 multiplied by n. So here, once we hit the nth plus 1 operation, we will have an array of size 2n, where n plus 1 elements are placed in the array. So we will not hit this on operation again until we place another n elements. You get me? Okay, look. Yeah. Yeah, we have n multiplied by on equals on. I didn't understand. Hmm. Um, T of n is just it doesn't need to be the exact number of operations expressed by n. It could be just an estimate, because we could argue, someone might tell me that this instruction, this plus plus, this is 2 instructions, not just one. Someone might tell me that, someone might tell me that I don't know, there is a hidden instruction in this, but the constant the T of n is just an estimate of the number of instructions expressed as a function of n. So when I say O of 1, like the first, we could agree that the first 16 operations are O1 because the array is not filled. Is not filled, so we will execute directly these two. So it's O1 because T of n equals just 2. We will just assign the value to the cell and increment the number of values in the array. So this is T of n is O1 because C here is equal to 2. 2 multiplied by 1. Or we could choose any constant that is above 2, and this would work. So when I wrote that n multiplied by O of 1, meaning that we have a succession that's of O1 operations, we have a sequence of operations that will execute just this portion, and we would not be concerned with this. It will just place the elements and increment the number of elements. So this O1 is just, it means that it's some C multiplied by 1. So this is On. It's n multiplied by C, which is On. You get me? Yeah. So we have a series of constant operations. We could just sum those constant operations. We have n constant operation. N constant operation is a constant multiplied by n, which is On. So overall, we will have 2 multiplied by On, which is just On, divided by n plus 1. We could ignore this constant, and we will have just O1. So in average, we averaged, like we estimated on average that a single push is O1, or rather, what you can imagine this at. So we agreed that we have a sequence of n operation where each will be O1. So each will be some C multiplied by 1, or rather C multiplied by n to the power of 0. And then the nth plus 1, where the array is filled, we will have to do an operation of On. So this On operation is some C prime multiplied by n, right? So we could see this as 1 plus 1 plus 1 plus 1 plus 1, etc. C prime, and we would distribute the C prime. It's like we paid for that On. You guys hear me? Did I disconnect again? No? Okay. So it's as if we paid for that n operations on the succession of n operations. So it's like we added this C. It's like when you pay a car on you pay for a car. I don't know how to say this in English. Translate. Wait. It's like you pay for something. You pay for a car on on multiple months. What is that called? Like you pay like each month. The bank will deduct some amounts from your. No, the interest, not interest rate. That's something else. But it's like the bank will buy you the car, and it will deduct a sum, an amount of money from your to pay for the car. Like, okay, there is interest or something like that, but you will pay. Yeah, yeah. Like you will be paying for the car on multiple months. Okay. So it's like we paid for that ON operations. It's like we distributed that ON operations on a succession. It's the same thing. You guys understand the analogy?
Yeah, got it.
Okay. It's clear.
Actually, I understood.
Okay, I will try to explain it to you later. Okay. Okay. So this is it. This is amortized complexity. We computed like on average that the complexity of a single operation would be O1. Uh, we had a succession of O1 operation, then one ON operation. So we averaged over all the n plus one operations to find that a single push will be on average n ON, pardon me, operation. So pop elements from the back. I will just finish this right now. Pop elements from the back. So pop will just return the last elements in the array and decrement the number of elements. But here we will do the inverse of the push operation. What I mean by the inverse is that if if the length of the array is if the length of the array is higher than or rather if length of the array over 4, so if the quarter of the length of the array is higher than the number of elements, then we will just resize the array to be half of the size. So what I'm saying is, if we have this big array, because we might have a succession of rather not a succession. We could have a mixed
Alternate.
sequence. Yeah, we will have an alternate sequence of operation where we pop and push. We don't know the sequence, what's the sequence beforehand. So we could have at some point we could have just like 3 elements in the array because we popped a lot of elements, and our array is like of size 16. So to not waste memory, if the number of elements is less than a quarter, we will resize the array to be half of what it is. So we will just half the size. And why we resize to half rather than the quarter, because if we resize exactly to the quarter, we could have just next another push. So if we resize to the quarter, we could have another push just later, and then we have another push, then another pop, then another push. So it will be on operations for each if we have a succession of push, pop, push, pop, push, pop, and we resize to the quarter rather than the half. This sequence of operation will bring each call to on, because we are no longer we don't have. If we do this, the sequence of previous operation will not be O1. Each operation here will be ON. Yeah, yes. If we resize to the quarter, we could find ourselves in this situation where we will resize each time we place a new element, or each time we pop. So rather than putting the size to exactly the quarter, we will just put the size to the half, so that we would avoid this succession of operations. This is clear. Yeah. No. This in pop. Every time in pop we are decreasing elements. So if we have less than the quarter of the the capacity of the array, we resize to the half. We resize to the half if we have less than the quarter. So this is still an ON operation. Pardon me. This is when we resize, this is ON. Because if we resize, then we are what we're doing is we are creating an array with size n/2. So we need n/2 operations. Then we have to copy the element, so n. So this is 3/2n, which is ON. Okay. So like push, once in a while we will find ourselves resizing the elements, and that resize will be costly. And like push, this operation should be amortized on the previous succession of constant time, because again, if we don't hit this case, or this condition is false, we will have just a constant time work. So okay, the good news is all this blah blah that I just said, you probably wouldn't have to deal with this. You could just use it. But sometimes, if you want to design efficient data structure, you could use this. Other than that, if you're familiar with generics, you could implement this data structure for any supported type, rather than because here the implementation supports only integer. But if you here we would pass the type as a generic, and we would create an array of object and cast it to type. So I hope this was clear, and if you guys are still up for it, we would at least start in you guys could try the quiz on your own, but I would like to I'd like to at least talk about range queries. Give me just a few minutes. I'm gonna drink some water. Okay. Okay, let's now talk about the data structure that is very, very core, I think, and it's not supported in the standard library. Actually, I was gonna explain row measure first. So row measure representation is that usually well a 2D matrix, like a two-dimensional matrix, is just an array of arrays. You could think of it as an array where each element is a row. Okay, so sometimes you need to represent a 2D matrix. Sometimes you need to represent a 2D matrix as a flat array, like a 1D array. This is quite common. So if we represent this 2D array as a single 1D array, so we will have each row. We will have the rows in succession. So we have the first row, then the second row, then the third row, etc. So if there is a way to access like elements as if this in the same way that we would access an element in a matrix, we could access it in this representation in a 1D. So any element in the 2D matrix, if we have an element in position ij, if we say that an element is in position ij, it means that it's in the row I, column j, right? So if we want to access it in this flat representation, then when we say the ith row, so in this representation, the element will be in the in position I multiplied by the number of columns. So if we have m columns, so we have I multiplied by m plus j in this flat array. So if we call this mat 1D and this mat 2D, then mat 1D mat 1D I multiplied by m plus j, where m is the number of columns in the matrix, is the same element as matrix 2D row I column j. And what is this basically saying is, to access the element ij, we just skip I multiplied m. So if we want to access this, we would just skip 2 rows and then access after that the jth element. So the element in position I equals 2, j equals 3 is just 2 multiplied by 5 plus 3, which is 10, 13. This is exactly that. M, the number of columns. So M here equals 5. Sometimes this is more convenient than than the 2D representation. And if we have an element, if we have this representation as an array, and we want to translate the indices to the 2D matrices. So if we have index, we have an element at position index, and we want to translate this single value into 2 columns, what we do is we just divide by m to get the row number, and the column number would be just index modulo m. So here it's 2 multiplied by 5, 2 multiplied by 5 plus 3. So this is position 3. So if we take 13 divided by 5, which is the number of columns, plus comma 13 comma 13 modulo 5, we will come back to the 2D representation, which is just 2 comma 3, which is exactly this. Okay, so let's go over to the more interesting topic of the lecture. So suppose that we have an array of array A, so an array of integers of size n, and a series of query q where each query is in the form LR. Each query is asking to sum the values in the range LR. So we have an array A with some values inside, and we have a series of Q queries where each query is expressed as LR. And this query is telling us to sum all the values from index L to index R inclusive. So this is straightforward, but what we're going to see is that this is a range query, meaning that we have queries on ranges, but the operation might not always be the sum. We will see later that we could implement efficiently operations like max, min, XOR. Certainly max and min are very useful. We could implement the products of a range efficiently without, of course, without looping over the entire range. So to answer these types of queries, we could just loop over the list of queries, and for each query we will take L and R and sum over all the values from L to R. Or rather sum over all the values from A bracket L to A bracket R, and we have so the complexity of this, I hope this is clear. The complexity of this is we have Q queries, so we will go over all the queries. And here in the parts where we sum up over the values, the complexity of this loop, worst case could be n if L equals 0 and R equals n. Worst case, the amount of work that could be done in this loop, it could be up to n. Okay, so worst case, this algorithm would run in OQ multiplied by n. we could get clever and pre-compute all the ranges, or try to remember answers for ranges that we already computed, so we don't compute the same answer for the same range. But this won't give a significant improvement because we have n multiplied by n plus 1 over 2 possible ranges. The query, a single query here is telling us, like a single query. Here we are answering in this part of the program. This is a single query. A query is asking us just to sum over the values from L to R of our array A and return the value. We just we have an array, and in each like we have this array A, like we have A here, and we want from 3 to 5. So a single query would be just ask us to sum from some L to some R. So here in the example here, L equals to 3 and the R equals to 5. So another query would be like you could check this, that 0, 1, 2, 3, 5, 6. So 8 plus minus 15 plus 12 would be would give us minus 17. Minus 12 and 8, it will be no, I think I made a mistake. 0, 1, 2, 3, 4, 5. Oh, 6, 7, 8. Here, this notation A6, comma 9 will give us just the sequence of value from 6 to 9, from indices 6 up to 9, and 9 is not included. So this is 9. This is the element at value 6, so it will give us this 6, 7, and 8. So a single query is just asking us to sum over the values in the array in a given range, LR. Is that clear? So a single query here, a single query will just ask us to sum over the values in A from indices L to R. So we just have to loop from L to R and sum over the values and return the sum or print the sum or something. We just have to compute. Okay. The syntax in Python. Here for you're talking about this line 3. L comma R. So if you if you like have like look, you have A.
Like tuple of lists.
Yeah, if you have A, this this means values from 0 to 1. 2 is not included, so the values from indices 0 to 1. So this is what it returns. Yeah. So if we put LR equals this, you could check L. We'll take the first value in the array, so L R. This is I don't remember what this is called, unpacking or something like that. I don't remember the exact term.
It's
But
in Java unpacking.
unpacking, yeah. Oh,
In
unpacking. Okay. In Java unpacking, I don't remember the term for Python. But what essentially we are saying that we could write this if you know JavaScript. This is maybe more familiar. So we could do this, and it's the same A. So it's just a way to assign multiple values to variables. We could write like VC equals 1, 2, 3. So yeah, in Python, in JavaScript, this is quite common in JavaScript. So you could assign in a single line, like you could like here A and B. You could do like A and B equal B and A. So you could swap the values in a single lines. A. Okay, so this is just the concept. I hope we could agree that this algorithm is O(n) multiplied by Q. So we have Q queries, and worst case, each query would be O(n). As I said, we could get a little bit clever. But the number of ranges in the array is n multiplied by n plus 1. So if we have a very, very large array, the number of ranges could be huge, and we could have a query for any array. So this wouldn't make a significant difference. So there is a simple. Is there a question?
Hello.
Yeah.
Okay, is it always the sum as query? Like sum of ranges.
The query is not necessarily a sum. The query could be min. We could have a min query, like we have a range LR, and we need to find the minimum in the range or the maximum in the range. But for now, the simplest form of query is the sum, and the sum is easier to compute. It has a simple data structure that we could use to compute the sum. But for the other type of query, it's there when we introduce like a main data structure that is called segment tree. Okay.
Okay.
Okay. So okay. So this problem, actually, if we just have the sum, this is very easy to solve. We could create an array called prefix sum that will contain the sum from of all the ranges starting from 0 to I. So this array prefix sum will be the same size of the array that we need to compute query on. So it will be the same size of A, and prefix sum, like prefix sum. Prefix sum I will be equal to A, or will be equal to the sum from it will be equal to the sum of the prefix of the array from 0 to I plus 1 here, I plus 1, because if we just write I will not be included. So it will be equal to the sum of all elements from 0 to I. Each value prefix sum I will be the sum of values from 0 up until I included, of course. So this is very easy to compute. This is a pre-processing step where we put prefix 0 equals to A0, and then we go in the range 1 to ln A, where each value, where in each position I, we will put prefix I minus 1 plus I minus 1. Pardon me. We will put prefix I equals to prefix I minus 1 plus I minus 1. So this will give us, this will create a prefix sum. We could try this. Random. So rather than just here is I. Let's just make the prefix sum of equals ln I multiplied by 0. So we are creating an array with 0 elements of the same size of I, of the same size of A. We put prefix 0 to be equal to the same the first element of I. And then we do from I in range 1 to ln I prefix I will be equal to the prefix I minus 1, so the previous value, plus A sub I. So, and we will have, we could see prefix I, prefix and I. So here at position 1, it's equal to, at position 1 in prefix, so prefix 1 equals I1. plus prefix 0, prefix I minus 1 would be 0. Wait a second. Okay. So we completely pre-processed the array and created a prefix sum for each position I. Okay. So when we need to compute for a given range, suppose that we need to compute for this range from this to this. So this is R and this is L. So from so here L equals 3 and the R equals 7 or rather yeah equals 7. So if we want to compute for this I equals 3 equals 7, 3, 4, 5, 6, 7. Okay. Okay. So if we want to compute the sum for this range, we have in the prefix array so we have the sum from 0 to 7 equals 108. We have prefix from 0 to 2 equals 45, 54. So what we have this. We have this sum and this sum. This is actually prefix for L minus 1. So to compute the sum of this entire range, we would just do prefix R minus prefix L minus 1. So we are removing this part from prefix R to get this entire sum in constant time. We don't have to sum over again. Is it clear? Or should I repeat? Yeah, every time we needed to compute the query, for each single query, we had to loop from L to R and sum the values, right? Yeah, but now with this prefix array, we could look up directly prefix R we could get this directly from the prefix, right? And we would subtract prefix L minus 1, and this would be the answer for the range query. This would be exactly sum but now we are doing this in constant time because we pre-process the array and we have the prefix arrays already in place. We just subtract from a prefix R, so we just subtract from the sum that we computed from 0 to r, we subtract the left side, and we have directly the answer for the query. We don't have to loop over the entire range. So it's a constant now. Answering the query is constant time. So we don't have to loop right now. We just take prefix r, and if I is superior to 0, we just subtract prefix al minus 1. So now answering a single query is O1. So the complexity of this program is here we added a pre-processing step of ON plus answering the range query, answering a single range query is O1, so we have Q. So the complexity of the entire program would be ON plus OQ, whereas initially it was ON multiplied by Q. So this is a significant improvement over the first approach. This is clear?
Hello.
Hello? Hey,
Maybe
Farad.
like O of
Yeah.
n or O of q, right? Based on the size of, like if n is greater than q, it is O of n, or if q is greater than n, it is O of q. O of n plus q.
Yeah, if you mean you're talking about the complexity.
Oh, yeah.
Yeah, if we could keep this as it is, like ON plus Q, or we could write it as ON as O max of NQ, meaning that it's ON O of the max of the both, because if Q, we don't know if Q is greater than N or N is greater than Q. So whichever of the two is bigger, it would be O, that biggest term. So we could write both answers would be correct. Most of the time people use this expression more like ON plus Q, especially in graph theory, like usually you write the complexity of the BFS as V plus E rather than the maximum. But it's sometimes you would see people write in the max, and of course here E, usually E is V, typically is V log V.
Yeah.
Or V could be as big as V to the 2. So you could write either of the two. This is much safer. Since you're a computer science student, this is much safer to write, but sometimes you could see this. It's not a very big issue. Okay?
Yeah.
Okay. So this is an example. Let's if you're not convinced so you could walk through the example, and it should be clear. The prefix array, as I had the question just earlier, this prefix array would work for some cases, for some operations like sum. Usually sum. XOR would work. Products, if you don't have null elements, it would work. But for min queries, max queries, this wouldn't work. So we have a more sophisticated data structure that we will look into right now. So we I will go on for like half an hour and we will stop. I hope you guys are not tired. Okay, I will not continue for much longer. So for 2D matrices, it's the same concept, but rather than computing like in the prefix array, in the prefix array we computed prefixes from 0 to I and used the prefix to sum to compute the sum over ranges. For 2D matrices, we have the same ideas, but instead of computing from 0 to I, we would sum from we would sum values of submatrices from the origin or from 0, 0 to whatever value like E I low G low. So we would create a matsum matrix that will contain all the sums from the origin to a given indices ij. So this matrix sum will contain in a single cell, in each cell, the sum of the submatrices starting from 0, 0 up to that cell. So the entire sum of all cells. This is very similar to I could write it up very easily. So equals by 20. Okay. Fine. Range 5. So suppose that we have a matrix. Let's just do 4 rows, 3 rows, and 5 columns. So this is for M into R. This is our matrix, and if we want to just compute this matrix sum, it would be very easy. We would just for starters we just create mat sum with the same dimensions. Here we created the matrix, and for I in range, so we have 3 rows. For J in range 5. Mat sum, or rather, mat sum I ij plus equals mat sum ij minus 1. J different to 0, so we add Okay. And then we loop and we add the values of the previous row. If I equals to 0, continue. Oh, I should have copied import copy maths equal copy dot copy m. So we copy m first, then we execute the code. And then we print. It's oh, I have overwritten that's overwritten m here. Well, m is not null right now. And then we execute the step to sum up. And then we print the matrix sum. So you could check that, for instance, this the sum of this submatrix is 21 plus 9 plus 0. It would be exactly this. 11 plus 6, 11 plus 6 plus 9 plus 16 plus 5. It will be exactly this. So how to create this is fairly easy. We just loop over the rows, loop over the columns. For starters, we do a similar processing like the prefix array, where the value at the previous position, like when we are in position I, or rather when we are in column J. So yeah, when we are in column J, we add the value at column J minus 1, and then add the value of add the value. Actually this is useless. Oh no. I didn't copy. This is correct. So we add the value of the previous column. Like if we are in J equals 1, we add the value at the previous column, J minus 1, and then we add the current value of M. And when we finish this loop, we add for each column we add the value at the previous row. So here at this column we add 16, which is the value previously. Here initially initially here we will have 13 plus 11, which is 44, plus 6, plus the value at the previous, or rather, 11 plus 30. Oh no, not 11 plus 30. We will have 5 plus 9 plus 11, which is 25. 25 plus 60, it will be 31. 25 plus 25. 25 plus 22 will be 47. What we're actually doing is we are adding the previous elements here, the previous elements in the same row. Then we add the current element, and then we add the value in the same column from the previous row. This might be confusing, but if you read through the code, it's not that difficult to figure it out. So you could figure out the code by yourself to write this on your own. With your own ideas, but why we are doing this? So, if we had uh, if we had range queries where we need to compute submatrices sum, like we have to compute a submatrix sum from I top, j top to I low, j low. What we do is we have already computed every submatrix originating from 0 to a position ij for any ij in possible in the matrix. So if we want to compute wherever the sum of wherever submatrix, what we do is we will take the value in matrix sum at position I low, j low. So by taking this position, we are taking the sum of the entire submatrix from 0 to I low, j low. So to get this specific submatrix, what we need to do is we need to remove this sum and this sum, and we could access this directly thanks to the pre-processing step. So we could access the matrix of the sum of the matrix that is beneath directly by accessing mat sum. So if the lowest column is I top, we will access I top -1. -1. We will stay in the same column, so j low. So if we remove this value, we are removing this entire sum. Just like we did with the prefix sum. And to remove this margin, we would just remove mate. So here we are at row I low, so we keep the same row I low. Comma j j top. minus 1. So j top is this column, this. So minus 1 will get us to this. And since we removed this intersection twice, we will add it again, so we don't double decrement this submatrix at a top minus 1, j top minus 1. So short case, if we pre-process the matrix, we could compute the sum of any submatrix in O1. And this is the formula. This is all warm up to the actual data structure. This is just warm up explanation, and now there's a real data structure called the range query. I think I'm gonna stop here so you guys can take a break. Thanks for joining, and if you have questions, you could ask me later. I hope the explanation was clear. And if you didn't understand something, you could ask me like an exact something that you didn't understand, and I would try to respond. But try to read the material, try to go over it, so that if there's something, maybe you just missed something, or I don't know. Okay, so take care. Take care next time. Okay, you could share if you have if you could upload it, you could share it directly from wherever you could put it on YouTube or on Drive. You could do whatever you want, because it would take me time to upload. Okay, so take care. I hope I see you next time. Bye.
Thank you, guys.
Bye.
All right, Neville. See you in the next session. Sure. So does anyone have recording of the last class? I think yesterday there was a session which I have already missed. Okay. Okay, then I'm fine.
I think I have first class recording.
Okay.
Okay. Okay.
Yeah, please share with me, Neville. All right, Neville, then I'm dropping. Yeah, sure.
Yeah, bye. Bye.